Welcome to this course on microprocessors. In this first module, we will lay the foundation by exploring the architecture of microcomputer systems, semiconductor memories, the architecture of the Intel 8085 microprocessor, and the operation and control of its different cycles. We will also cover the instruction set, addressing modes, and basics of assembly language programming. By the end of this module, you should understand how a microprocessor functions at its core, how it communicates with memory and input-output devices, and how instructions are executed. Section 1: Introduction to Microcomputer Systems. A microcomputer system is built around a central processing unit, or CPU, which is the brain of the system. It performs arithmetic and logic operations and controls the flow of data. Key components of a microcomputer system include: CPU executes instructions and coordinates activities. Input, output devices, these allow data to enter or leave the system. Examples include keyboards, displays, and sensors. Clock provides timing signals that synchronize all operations. Memory stores instructions and data temporarily or permanently. Bus architecture components are connected by three main buses: the address bus, the data bus, and the control bus. The address bus carries the address of the memory location or I/O device being accessed. The data bus carries the actual data. The control bus carries signals that specify whether the operation is a read, write, or some other control activity. To prevent multiple devices from driving the data bus at the same time, tri-state logic is used. This allows a device to be in one of three states: driving a logic 1, driving a logic 0, or being electrically disconnected. Section 2: Semiconductor memories. Memory is critical for microprocessor operation. Let's look at its development and types. Semiconductor memory has evolved to provide high-speed, compact storage. The internal structure consists of memory cells arranged in rows and columns, with decoding circuits selecting the correct cell for access. Timing diagrams show the relationship between control signals, addresses, and data during read and write operations. Different types of semiconductor memories include: MROM, masked ROM, programmed during manufacturing. ROM, read-only memory, permanent storage. EPROM, erasable programmable ROM, which can be erased by ultraviolet light. EPROM, electrically erasable ROM, erased and reprogrammed electrically. DROM, dynamic RAM, which stores data in capacitors and requires refreshing. Section 3: Architecture of the Intel 8085 microprocessor. One of the most widely studied 8-bit microprocessors is the Intel 8085A. Pin description: the chip has pins for power, clock, control, address, and data. Some pins serve multiple purposes depending on the mode. Internal architecture: the 8085 contains an arithmetic and logic unit, or ALU, general-purpose registers, a program counter, a stack pointer, instruction decoder and control circuitry, and buses for data and addresses. The ALU performs arithmetic and logical operations. Registers temporarily hold data. The program counter tracks the next instruction to be executed. The instruction decoder interprets each instruction and generates the control signals required. Section 4: Operation and control of the microprocessor. The 8085 works through different machine cycles. Opcode fetch cycle: the microprocessor fetches the instruction code from memory. Memory read/write cycle: transfers data between the CPU and memory. I/O read/write cycle: transfers data between the CPU and input/output devices. Interrupt acknowledge cycle: handles requests from external devices. A state transition diagram shows the sequence of internal states the processor passes through during these cycles, guided by clock signals. Section 5: Instruction set and addressing modes. The instruction set of the 8085 can be grouped into categories. Data transfer instructions move data between registers, memory, and I/O devices. Arithmetic instructions: addition, subtraction, increment, and decrement. Logical instructions, AND, or XOR, compare, complement. Branch instructions, jumps, calls, returns, conditional and unconditional. Stack and machine control instructions, push, pop, halt, enable, interrupt. Addressing modes determine how the CPU identifies the location of the operand. Common modes include immediate, direct, register, and indirect. The execution of instructions can be represented by flowcharts, showing how control passes through different stages. Section 6, Assembly Language Programming. Assembly language is a low-level language that uses mnemonics instead of binary opcodes. Assembler directives provide instructions to the assembler but are not executed by the CPU. Examples include defining constants and reserving memory space. Simple programs illustrate data movement, arithmetic operations, and branching. Subroutines allow code reuse, and parameter passing enables flexible function calls. In this module, we examine the fundamentals of microcomputer systems, the types of semiconductor memories, the Intel 8085 architecture, its operation cycles, the instruction set, and basic assembly programming. These concepts form the building blocks for understanding more advanced topics in microprocessors.